Assalamu alaikum. Uh, in this lecture, we will study another topic that is that is called demodulation or detection of binary signals in Gaussian noise. And now this is from the chapter 3 of the book Digital Communications by Sklar. Uh, I want to show you some overview before this lecture, that how we're gonna, you can say, relate our this lecture with our previous lectures. So as far as our previous lectures is concerned, we have started our digital communication course from the basic probability and random process definitions. Then we're gonna move on to and the random process that are gonna involved in digital communication, and the probability that involved in digital communication. Then have moved to the other topic that are called the digital modulation techniques that we're gonna use in digital communication. And then we have made an then we have already you can say study about the various topics like linear codes and different modulation digital modulation techniques. And then we have studied you have already studied in previous lecture regarding the linear codes. Now as far as linear coding is concerned, that when we are studying the introduction to a source coding, then we have studied the linear coding as well. Now we're gonna move on to another thing, that how we're gonna get this you can say the data, that the binary data, how we're going to detect that binary signal that we have created using the digital modulation techniques, and you can say the coding techniques that we have used in source codings. Okay, so as far as this topic today is concerned, we're going to study about the detection of the binary signals in Gaussian noise. I'm going to let you know what is a Gaussian noise and why we are considering a Gaussian noise here. Then we're going to study about the match filters and correlators, and then we're going to study Bayes decision criterion, maximum likelihood detector, and error performance. Please remember, might be this lecture will going to end with in some topics, and might be I will cover this in another lecture, because we have a limitation of lecture timings here as well. So might be but overall you can say this is the part, these are the part that we're going to cover as far as demodulation or detection of the binary digital data that we are using is concerned. So we're going to study today, and this is the block diagram I showed you in previous lectures, or in many lectures as far as digital communication is concerned. This is a whole block diagram as far as digital communication is concerned. This is a representation of a digital communication you can say transmission here. Now we're going to study these two blocks here, and this one is the demodulation and sample here, and then we have a detector here. So we're going to study from in this lecture, or might be we'll cover for in another lecture about these two blocks here. So see here, what is basically a demodulation and detector here. We have created the transmitted waveform using a analog message signal. Then we have performed the sampling. Then we have made you can say, then we have quantized our signal. Then using different digital modulation technique and encoding technique, we have encoded our data in terms of digital data, and then using modulation technique we have sent our transmitted waveform. Now you see that as far as this detection is concerned, this detection gonna be performed at the receiver end. And here you see in this block that the block diagram that is on front of your screen, you can see that when the transmitted waveform is passes through a channel, it will gonna be having an additional a white Gaussian noise here, and we're gonna received a waveform here that is basically is the you can say the addition of the transmitted waveform and AWGN or a white Gaussian noise here, and the received waveform is basically is the addition of these two things, the original transmitted waveform and the noise from the channel. And now using this, what we're gonna do as far as demodulation and detection is concerned, we're gonna pass through this through a frequency down conversion, then we're gonna pass through a receiving filter here, and then we're gonna equalize perform an equalizing you can say filter here, and then using the threshold comparison or a decision detecting device or decision making device, we're gonna get our message symbol or channel symbol here. So now this is the two step in the demodulation or detection of signals are concerned here. This is a frequency down conversion, and this is for band pass signals here, and this is for compensation for signal induced ISI here. Okay, now the digital receiver performs two function. First one is to the demodulation, to recover a waveform to sample at t is equal to nt, so that we can get our original message signal, and then it's gonna perform a detection that is gonna be this is called decision making process of selecting possible digital samples. Now see here, this is a block diagram, and this is a complete or a detailed block diagram as far as previous topic is concerned, that previous thing that we are considering here as far as detection and demodulation is concerned. So this will be a block diagram here, you see here, this is from the book. Okay, so might be you see, I think it is clear here. Okay, so this will be our SIT transmitted waveform here, and this is our summer here. Okay, now we are, you can say, we are providing a detailed overview of this block diagram actually, with all the components having. Okay, so then we're gonna pass through a frequency down conversion, then we're gonna input this to a receiving filter, then through an equalizing filter, and then through a threshold device, and then we're gonna get our original signal back here. Now this part, that three blocks, frequency down conversion, receiving filter, and equalizing, that is to waveform to simple sample transformation here, that we're gonna make the signal to nt here, the sample signal here. Okay, now see here, this one as far as frequency division is concerned, frequency down conversion is concerned, that will be for band pass signals here, and that receiving filter here, that will be for baseband pulse, that will create a baseband pulse here. Here we're gonna have a baseband pulse that will gonna be like this one, AIT plus N naught T here, that we're gonna call it a Z of T here. Okay, as far as this, the received waveform that we are receiving here, you can say at the receiver, that is that we will call it R of T here, and that is a that is, you can say, multiplication, because this will be gonna will have a multiplication of two signals, SIT and AWGN here, that is coming from the channel here. So the mathematical representation as for the channel noise and the transmitted waveform is gonna be represented like this, where R of T will gonna is equal to the S of IT, that will gonna convolve with H of CT, that is a channel response plus N of T here. Okay, so now we're gonna move on to other thing. Now this is the detection of a binary signal in Gaussian noise here. These are the I think you have gone through these kind of figures in your lab trainers. I will not gonna go in detail about these you can say the spectrums here. So I'm gonna, because we are considering a theoretical or mathematical representations here, so we will wanna only talk about the mainly or not about the, you can say, the how we're gonna get the theoretical detection of the binary signals or demodulation of the binary signals here. So, and now this detection of a binary signal in Gaussian noise can be performed. For example, we have to make an analysis. So for example, for any binary channel, the transmitted signal over a symbol interval 0 to 2t, please remember that the receive waveform that we are using is in terms of a symbol here. So and the duration of that symbol interval is 0 to t here, and that will gonna be represented like this. This SIT is the actually is our transmitted waveform that we have received at the receiver, and that gonna be represented like this, S0t, where Z is where this symbol gonna start with have a time duration start from 0 to t for binary 0, and S1 of t for for the symbol binary 1 and have a bit duration starting from bit symbol interval starting from 0 to t here. Now the received signal RT is degraded by noise n of t from the channel and possibly degraded by the impulse response of the channel HC of t, and we're gonna mathematically represent this thing as far as our channel noise is concerned and our channel response is concerned with the transmitted wave. We're going to represent mathematically with this signal that is called R of t, and this R of t is equal to S of I of t convolved with HC of t, that is the impulse response of the channel here, and plus the noise, addition of the noise here, where this I of t is the transmitted waveform, and we are using two symbols 0 and 1, so I will be going to stand for 1 and 2 here. Now, where n of t is assumed to be 0 mean a wide Gaussian noise process here. Okay. Now, for ideal distortionless channel, where hc of t is an impulse function, and convolution with hct produces no degradation as far as ideal distortion is concerned. For example, we are saying that we are considering an ideal distortionless channel, then h of ct is an impulse function and convolution with hc of t produces no degradation, so r of t can be represented like this. Okay, now see here, we are getting s of t it original here, but we are talking about an ideal distortionless channel that is not affecting our transmitted waveform, but we have only this noise that is coming from other sources here, and we are going to represent it with n of t here, but there is no effect as far as impulse function of the channel is concerned here. Okay, now moving further, this is the example for this is the block diagram for detection of a binary signal in Gaussian noise. Here we have a transmitted waveform, and because we are representing now this thing here, we're gonna make assumption according to this mathematical expression, or for this statement here we are considering ideal distortion as channel now. So for example, if we are considering an ideal distortion channel here, then the block diagram for the mathematical representation for this will gonna be look like this, where si of t will gonna be multiplied with this n of t here, and we don't have any thing involved from the impulse function of the channel here, so we are getting r of t here, and that will gonna go through this h of t and creating a z of t here, and this is the bit symbol duration here, and that z of t will gonna go through this pulse shaping here, and then we are receiving this s of t again here. Okay, the transmitted waveform here. Now the recovery of the signal at the receiver consists of two parts. Now first one is called filter, that gonna reduces the received signal to a signal variable that is called z of t here. Okay, and second part is called is detection or decision circuit here. Remember, this z of t here is gonna represent, is called the test statistics here, that gonna be performed for that is gonna be, you can say that gonna be act on the transmitted wave when it gonna pass through the channel here. Okay, now the detector or the decision circuit here we're gonna compare the z of t to some threshold value, and we are representing this with r0. Okay, that is that zt will gonna compare this value with some threshold value, and if it gonna be when it gonna compare this value, it will gonna create two symbols where h1 and h2 are the two possible binary hypothesis values are there for the symbols here. Okay, now moving further, so see here that we're gonna see the what is the functionality of the as far as receiver is concerned. The recovery of the signal at the receiver consists of two parts. First one is, I told you in block diagram that it will gonna first part is that that the waveform to sample transformation here, the demodulator followed by a sampler here. At the end of each sample duration t, prediction point yields a sample zt called test statistics. Okay, and that zt will be equal to ait plus n naught t here, where I gonna be for 1 and 2 here. Now this zt is basically, it was created, these are the test statistics that are coming from our the demodulator block. Okay, that is followed by a sampler here, and here these zt this zt producing an ait here, which are the two hypothesis value that we have getting in previous slide here. So where IoT is the desired signal component from the hypothesis value here, and now T is the noise component here. Okay, now see here, the detection of the symbol. Assume that input noise is a Gaussian random process. For example, we are considering the input noise that is acting on our input signal is a Gaussian random process, and receiving filter is linear. Then we're going to represent with the function, probability function with like this one, that will be p n naught, that will be equal to 1 over sigma naught under root pi exponential minus 1 over 2 into n naught over sigma square over 2 square. This is from the Gaussian distribution function here. Okay, so this is the behavior if we are considering input noise as a Gaussian random process, then it will have a probability density function like this. Okay, so and then output is another Gaussian. If for example we have assuming input noise is a Gaussian random process, then the output is another Gaussian random process that will gonna look like this, with where pz slash s naught will be 1 over sigma naught under root pi exponential minus 1 by 2z minus a naught over sigma square over square here, pz over s1, that will be gonna give this one here, this mathematical expression here, where sigma square is the noise variance here. You know that sigma square is the noise variation when we have studied about the random processes in communication systems or in digital communication systems that we are using. Now see here, the ratio of the instantaneous signal power to the average noise power at a time t, output of the sampler will gonna be like this, will gonna be defined like this, S1n. This is the ratio. This is called the instantaneous signal power to the average noise power, and that's going to be represented with ai square over sigma square. This is our input, possible input here, divided by the sigma square is here, that is coming from the probability density function here. Okay, now see, we have to need to achieve maximum s signal to noise ratio here, so that the receiver will not gonna be you can say we're if we have a each maximum you can say signal to noise ratio, then we don't have we will not face any kind of problem as far as our receiver is concerned. Now as far as this thing is concerned, we have to find filter or transfer function h naught f here. Now to objective for this thing, for achieving or for maximizing signal to noise ratio, we have to find a filter transfer function h naught f. Now expressing signal AIT at filter output in terms of filter transfer function. Now we are representing for example this AIT signal here, that is our given data here, that will gonna that should be having a maximized value of signal to noise ratio here, so that will gonna be represented in terms of a transfer function like this, where we're gonna represent this transfer function in terms of this function s of f here, that where s of f is the Fourier transform of the input signal here, and this is the transfer function. So this is gonna be represented with this Fourier transform here. Okay, output power can be expressed like this one, where sigma square will be n naught over 2 here, and that will gonna be minus infinity to infinity h naught f square df here. Okay, just integrate the, you can say, the mod of the transfer function here, square of the transfer mod of the scale function here. Now expressing signal to noise ratio here, we're gonna use this one divided by this one, because we have I told you that what we are taking here, what we are considering here, we are taking this thing, this one, or make an approximation from this thing. I'm gonna show you here, just wait a second, from this thing. Okay, from equation 3.45 we have AIT this one and sigma square this one, so we are putting this one here. Okay, now moving further, for HF is equal to H naught F, to maximize signal to noise ratio, we're gonna use Schwarz inequality. I hope so that you have already know about the Schwarz inequality in your calculus or some other courses are concerned, but if you don't know, then we're gonna only know about this mathematical representation. It's gonna be represented with this thing, that whenever we're gonna have two functions integrating and multiplying together, and we're gonna integrate them minus from minus infinity to infinity with the mod square here, that will be less than or equal to first mod of the first function square when we are integrating, and then we have integration with the second function here. So we're gonna split them together. This is called Schwarz inequality as well. Now equality holds if f this from this inequality we come to know that if f1 of x is equal to k f2 of x. I will gonna let you know this what this mean of this steric here, where k is an arbitrary constant and steric indicates complex conjugate. Here f1x and then f2x, this steric will gonna represent some conjugate, and where this k gonna represent an or any arbitrary constant here. Now associate h of f, the transfer function here, with f1 of x and s of f here. This s of f is the frequency or a Fourier transform of the incoming signal with f2 of x to get this one here. Okay, remember this one, h of f, s of f. Here we are getting this one square, then this will be equal to putting this one for f1 of x here, we are getting the inequality, and 3.49 becomes this one here. Now we're gonna substitute this one in 3.48. In previous example I'm gonna show you what is 3.48. This was our 3.48 here. So when we're gonna put this one in 3.48, what we're gonna get here, we're gonna get signal to noise ratio that will be equal to less than or equality, using because we are using an inequality theorem here, Schwarz inequality theorem, that will be equal to 2 over n naught minus infinity, starting from minus infinity, integration of starting from minus infinity to infinity mod of s of x square into df. Okay, so so the maximum S1 at S signal to noise ratio will be less than or equal to T over n naught. From this approximation, please remember we are making an observation that maximum signal to noise ratio for the T duration of the symbol here will be less than or equal to T E over n naught, where energy E is the energy of the input signal here. Okay, now thus signal to noise ratio depend on input signal, okay, energy of the input signal, and power spectral density of the noise. Okay, this is basically this n naught will gonna represent the power spectral density of the noise coming from the power spectrum of the noise. Now see here, and this E can be found using this you can say function s of f square df here. Okay, this is the energy E of the input signal. We can find the energy E of the signal using this now, and you see here that this signal to noise ratio does not depend on the particular shape of the waveform here. So equality for maximum this signal to noise ratio holds for optimum filter transfer function h naught of it. For example, how it gonna hold for more optimum filter transfer function h naught, h of f here, which for example such that we are considering h of f is equal to h naught f, that will be equal to k into s convolved with this is the s conjugate here actually, f with e minus j 2 pi ft, where h of t will become, for this expression will become this one. This will be the inverse Fourier transform of this one here. Okay, so for real valued signal we're gonna represent h of t like this one here. So from this observation we see that signal to noise ratio does not depend on the particular shape of the waveform. It's gonna depend on the input energy signal and power spectrum density of the noise here. From this one we're gonna design our h of t here, the impulse response of the filter here, that is gonna be represented with this one. Okay, so now the impulse response of a filter producing maximum output signal to noise ratio is the mirror image of the message signal delayed by symbol t duration here. The filter design is called a match filter. This is called a match filter actually, that we have designed from the approximation that we have used. Now this is going to defined as a linear filter designed to provide the maximum signal to noise ratio at the output for a given transmitted waveform. Okay, now moving further, we have there is another topic that is gonna be called correlation realization of this match filter that we have observed previously. And a filter that is matched to the waveform s of t has an impulse response that gonna be represented with this one. Okay, and h of t is the disabled version of the mirror signal rotated on the t is equal to 0 axis of the original signal waveform here. This is a s of t signal here, and this is s of minus 3. This is a mirror image of the signal here, and where this h of t gonna represent now like this here. This h of t is the delayed version of this massive signal here. Okay, impulse response of the match and that is also the impulse response of the match filter here. Okay, now moving further, this is basically from this observation, the graphical representation, we come to know another observation that this is a basically a causal system. Recall from your signal system course that a system is causal if before an excitation is applied at t is equal to t, the response is 0 for minus infinity to t till then t here, and you can see from here as well, and that we are not getting value before t here, capital T here. Okay, the response is 0. Okay, the signal waveform at the output of the match filter will be this one, where z of t will be r of t convolved with h of t here, and that will gonna be represented with integration starting from 0 to t. If some, this is a definition from the convolution theorem here. Okay, now substituting and h of t to gonna for in this one, we're gonna yield this signal. Now we're gonna solve this using the this property, and putting t is equal to t, we're gonna get this one here, z of t here, this one. Okay, so after getting z of t, then we're gonna define the function of the correlated and match filter at the same time. Now see, for example, we have r of t here, we have an s of t here, and we have already get how we are getting this z of t here. So for if we have get this one mathematically, we can draw it in a block diagram like this. We have r of t, we have s of t here, that's gonna pass through this 0 to t dot dt, and that is giving z of t, because z of t is coming from this one. Okay, integration starting from 0 to t, r of tau multiplied with s of tau here. Okay, and now this one will be si of t here, and then we have another this thing signal here, that will be s of t. When we're gonna have an n of t here, that will be we are having r of t here, and we're gonna compare both of them together, compare a and b here. Okay, this one is the function of the correlated and match filter. This one is from the approximated you can say calculations, and this one is our you can say original thing that we're gonna face in our practical scenario. Okay, so comparing both of them, we're gonna get z of t here, and we're gonna get z of t that will be equal to this value here. From a we get this, and when you're gonna get this one, we're gonna put zt here instead of t here. Then we're gonna solve from b, we get this thing here, and when we're gonna put this h of t here with this one, okay, using some mathematical aspect. Now at the sampling rate t is equal to t, we're gonna make more t here, and this will be, we're gonna get this zt will be equal to z bar of t, comparing both of them together. Now this will be the mathematical comparison as far as two systems are concerned. First one is a and b here. Okay, so we are getting this one. So this is about, you can say, the detection as far as the waveform is concerned, by comparing our using the match filter or correlation realization of a match filter here. Now in further lecture, we're going to discuss more about this detection of the you can say the detection of the this received waveform here in our next lecture.